example of quantitative electrolysis that involves solutions. In the 3 questions I gave you, the first one, which was question 5, involved calculating mass. I'm not going to go through that question because it's so similar to the Khan Academy example that you were given, and I don't think anyone had a problem with it. However, I did have a couple of messages about the ones that involve solutions, so I'll go through one example. So that would be question 6 of the ones involving solutions. And then that should allow you comfortably to check up on your question 7, just in case you got that one wrong. Okay. Now I'm going to go through this question in super detail. In other words, I'm going to explain the electrolysis setup. I'm going to explain exactly what's going on at the electrodes and stuff, just to give you a little bit more of a complete picture. Now, of course, you don't need to do any of that if you're answering a question like this in the exam. So let's read the question. Calculate the volume of hydrogen produced at RTP, which is room temperature and pressure, when a concentrated aqueous solution of sulfuric acid is electrolyzed for 15 minutes using a current of 1.4 amps. Now, something to draw your attention to here is that you have a slightly more complicated you have more complicated events going on when you are electrolyzing solutions, okay, aqueous solutions. It's not as easy as when you're electrolyzing a molten substance because you've only got 2 ions to think about. But when you're dealing with an aqueous solution, you've got to remember that means that it's effectively dissolved in water. And what water does naturally, it breaks up into its component ions. So you get hydrogen ions and hydroxide ions floating around in this solution, which will be mixed in, let's say, with the other ions that you're talking about, okay? So you've got water breaking down into hydrogen ions and hydroxide ions. And remember, this is something that's going both ways. So that's going on in there. And what else is going on in there? Well, you've got to deal with your sulfuric acid. Now, sulfuric acid is H2SO4. We should all know that. And this will be breaking down into its ions. You could say it's been ionized. And we'll be obviously producing hydrogen ions and sulfate ions. You should know that sulfate ions are 2-, should be stuck in your heads by now. Now that's not quite right, is it? We can see we've got a problem here with balancing. Every time you ionize this, you're going to be producing 2 hydrogen ions, like so. So effectively, the reason why there is an added layer of complexity when you're talking about aqueous solutions is because you have multiple cations and anions, okay? Now in this case, the cation is actually the same. But the anion is different. We've got hydroxide ions there and ions here, okay? But we have 4 different ions floating around in this aqueous solution. So we need to think about, well, what's actually going to happen when we put this in the electrolytic cell. So effectively, in our electrolytic cell, we've got all these ions. Now we've got to think about what is going to go where, okay? So what's going to go to the cathode and what is going to go to the anode? Well, although the terminology is confusing, we should now know that cations are positive, okay, because cats have pores, and they will go to the cathode, okay? So these ions here are going to this one here. This is the cathode. I'm just going to put C there, okay? So these ions, and now we don't really need to worry about what's going there because in both cases here, the cation is hydrogen. So hydrogen is going to be going to the cathode. So we can write down what's going on at the cathode now. Excuse the slow writing. I'm writing with a mouse. I will one day get a touch screen. So we've got the cations going there, and what is going on there? Well, they are going to. Well, you tell me what's going to happen here. That's right, they're going to produce hydrogen gas, okay, remembering that hydrogen is diatomic, okay, therefore you're going to need 2 ions going in to make a molecule of hydrogen. I haven't shown what's going on with the electrons here, but if you've got 2 positive charges, then effectively what's got to happen there is you've got to gain 2 electrons to neutralize that and make the atomic form, okay, so I should have plus 2 electrons here. I'm giving myself enough space. This should be plus 2 electrons. Now, why isn't it not just plus 1 electron? Remember, you've doubled up the number of hydrogens here, haven't you? So it's plus 2 electrons. Now, what's happening at the anode is slightly more complicated, because I'll do this in blue now because I'm doing all the anode stuff in blue. So we've got 2 anions here, haven't we? Okay, we've got 2 anions. So you've got to decide, well, which one of these are going to take preference and actually be the ones to be discharged at the electrode. Okay, and the best thing to do here is to probably learn this rule. There are various probably different rules. Some people will look at reactivity series when they're doing this, but I would remember the rule that you're going to have a preferential discharge for a halide. That will be the one that would be preferred. So if we had electrolysis of sodium chloride solution here, that would be relevant. But we don't have a halide here, okay, so that's not relevant. Then the next would be a hydroxide before any other negative ion, okay? Hydroxide before any other negative ion. So we don't really need to go past that, those 3 points there, okay? Because we've got hydroxide and then we've got another negative ion here in the sulfate. So what this means is, according to this rule, the hydroxide will be the one that is being discharged, okay? So we're going to deal with the hydroxide now. Okay, so what's going to happen here is we've got the hydroxide ions. We've said that they're going to be the ones that take preference. And this is slightly more complicated, but once you've done it once, you should remember, okay? Now, what do you think this is going to produce? Well, it's going to produce oxygen gas, and it's going to produce water. And it might just be beneficial if you just remember that to start with, before you really try to understand why. Now, obviously, this doesn't make any sense at the moment. Nothing's balanced here. This wouldn't be possible, so you need to make some changes, okay? So we've got 2 oxygens, so I could put 2 there, for example, okay? Oh, actually, we had 3 oxygens, so that's a mistake straight away. So I'll put 4 here. And what that means is we have now 4 oxygens left side, 3 oxygens right side, so we need to make an adjustment. We need a 2 in there. Now, has that messed things up, or are we correct now? Let's have a look. So we've got 4 oxygens, 4 hydrogens. We've got 4 oxygens, 4 hydrogens. So we're all good there, okay? But what we are missing, which is perhaps the most important stuff we're covering in this topic, is what's happening to the electrons, okay? So here, in order for this to happen, you're going to have to lose a certain number of electrons, aren't you? Okay, and because we got 4 minuses there, effectively on this side, there will have to be a loss of 4 electrons here in order for that to take place, okay? So oxidation is loss of electrons. So what's happening here is oxidation, and reduction is gain in electrons. So what's happening here is reduction, and it's worth us putting that in. Now, I think it's worth us delving a little bit deeper here and truly understanding what is going on. Remember, any redox process is going to have the number of electrons lost and gained to be equal. So if I was going to make this into a full redox equation, which I will do now, although it's not necessary for the question, it's actually irrelevant for the question, but let's do it anyway, okay? You need to have 4 electrons gained here, so hopefully you understand that quite simply you'd have to double that. Now, why don't we actually write out that full redox equation now? You will have 4 hydrogen ions on the left-hand side of your equation. You will have 4 hydroxide ions on the left-hand side of your equation. You don't need to now include the electrons. They are dealt with, okay? Because effectively they're cancelling each other out. So then you've got your line representing the reaction, and you're producing hydrogen gas and oxygen gas and 2 molecules of water. Now, I've missed something out here because things won't make perfect sense here. Okay, what I've forgotten to do is, remember, I doubled everything up here, so I should be producing 2 molecules of hydrogen gas for every 1 molecule of oxygen, okay, or 2 moles of hydrogen for every 1 mole of oxygen. Okay, and obviously we're producing water at the same time as well, but this isn't a vapor, so this is not bubbling off. Okay, so let's just check everything's okay. We've got 4 H's. We've got 8 H's on this side then, okay, and we've got 4, 8 here, so that all makes sense. And then we've got 4 oxygens here, and we've got 2 4 oxygens here. So this would be our full redox equation. I really think it is worth us doing that because it gives you a true impression of what's really going on here, and also gives you the kind of proportions of things that are being produced at the cathode and anode. Now, we've done so much background information there that hopefully it's aided understanding, and I've actually kind of forgotten what the question was about. So let me make all this a lot smaller, and we'll move that out of the way, and we'll actually crack on with answering this question. So I've put that in a small box over there. We may be referring back to parts of this while we're working through this question. In fact, what I'm going to do, I'm going to stop the video there because I'm terrified that it's going to crash and I'll have to do everything again. And we'll continue the calculation in the next video. See you in a second.